Without taking much of your time, just let me briefly introduce Dr. Anna. Uh, as such, she is very young, but she is one of the global leaders who is working in the area of sustainable construction engineering. She has extensively worked in Portugal, Lisbon, and right now she has even worked in Brazil, and right now she's working in UK. So in the Liverpool John Moore University, her core domain of research is the sustainable construction materials, their durability and performance evaluation, and what ways they can be given to the industry. So they are more focused towards industry-based solutions rather than only the research-based solutions. So I requested her in her presentation, over and above what she wanted to brief about the technical background, as more number of students are there whom I want to benefit. So let us see that, okay, if she can help you out, that what kind of support or what kind of challenges are there in the developed nations and how best we can do. Primarily, she is a specialist in the area of structural engineering. So she had extensively worked in that particular core domain as a consultant, and then she had enough number of publications, around 40 odd. The best part is she is also editor for one of the ICI journal, ICE journal, right? It's a journal of sustainability. Then she had enough number of projects which cost more than around $1.9 billion, million dollars, and she is also working or associated with the European Union, where she is consultant for energy efficiency for the building related projects. So I welcome you, Anna, once again formally to VNIT, and I hand over the session to you. I wish you will make the session very interesting to all the listeners.
So good afternoon, everyone. Thank you very much for this lovely introduction, and thank you very much for VNIT. VNIT really knows how to welcome a person. Thank you, especially Professor Raul. So I will start my presentation by talking about what we do at our research institute, what we can offer. We are always keen to develop international partnerships. And then I will give some examples, in fact, 2 case studies on the importance of the development of new bio-based solutions. One example is a structural example, and another one is energy efficiency issue in several buildings. So did you know that you can have better durability and indoor environmental quality for free if bio-based construction solutions are used? Did you know also that bio-based building materials continue to store carbon sequestered by trees and other organic materials? So this is what we do at the Built Environment and Sustainable Technology Research Institute. So we develop and optimize bio-based solutions to increase buildings' energy efficiency, durability, and to optimize agrothermal behavior using performance-based design methods, to incorporate industrial byproducts, life cycle assessment, life cycle cost also. We develop sensor technology for structural health monitoring, new and existing construction solutions, and sensor optimization for human well-being. And finally, we test all these products in real scale buildings to monitor behavior and optimize building materials. So our team is bonded by a unique goal, which is to develop novel bio-based multifunctional systems to provide a solution for significant energy savings, structural durability, as well as indoor well-being and comfort. And we design bio-based materials by tackling moisture buffering while ensuring the right chemical and mechanical properties to produce smart behavior that in the future will feed the building management system. So these are some examples of the products that we develop at our labs: internal thermal insulation composite systems, earth-based bioproducts, cork-based bioproducts, and self-healing bioconcretes. So we develop these at a laboratory scale, and then, of course, we need to test those new materials at a full scale to understand what is the real behavior. So fortunately, we have 3 full-scale eco-houses in our campus designed to standards from the 20s, from the 70s, and at the present day, fully that you can monitor using sensor technology, not only to check the behavior of those materials, but also to check different indoor environmental conditions. So we use this to test and develop new green technologies and new building methods, which is very suitable for the industry, because if the industry wants to develop a new product, then of course the industry always wants to test in the real performance of this product. And this is why we always work together. We develop industry collaborations, because we have the opportunity to develop real scale tests. So these are some ongoing research projects at Liverpool John Moores University. Optimization of bio-based building materials using image analysis methods, indoor air quality regulation through the usage of eco-efficient mortars, and this is a project in partnership with Nova University of Lisbon in Portugal. And for example, this second project here that I mentioned is about the development of bio-based materials that you can use as a refurbishment solution to put indoor, so it can absorb the excess of volatile organic compounds. The third one is optimization of bio-based materials using real-time monitoring of the moisture buffering behavior. And biocrete, self-filling bioconcrete with protection of reinforcement against corrosion. And finally, development of novel multifunctional bio-based insulation systems with smart materials for building refurbishment. So what we are doing, we are also developing bio-based solutions that can have the ability to absorb the excess of moisture indoor. I know that you don't have this problem here, but in Europe we have, like it is very often during the winter. We have in our houses more or less 80% of relative humidity, which is to higher level, and it leads us to several health problems, and it costs a lot for the National Health Service. So UK wants to reduce the problems and the sick building syndrome. So we develop solutions that can be able to absorb the excess of moisture and simultaneously, via of an exothermal reaction, release heat in a passive way. So it can also increase the thermal comfort for free. So bio-based multifunctional systems are a solution for significant durability and energy savings, and the talk includes some developments made in this field. Did you know that in Europe, repair and maintenance of existing structures cost around 40 to 60% of the construction budget, where the reinforced concrete represent a major relevance? Only in UK, 550 million pounds are spent per year on the maintenance and the repair of concrete infrastructure. So this is a major issue. And the steel reinforcement corrosion affects the service life of the reinforced concrete structures, which means that the economic impact could be reduced by better evaluation of the life cycle of the concrete structures and using durable concrete materials. And here I would like to emphasize the importance of developing low embodied carbon and low embodied energy concretes. So performance criteria makes possible to specify desired functions of the structure and building construction solutions. And this is mainly used for durability issues and energy efficiency purposes. However, the use of performance-based design needs always reliable information regarding the data of the involved materials. So the first case study that I will present here is the rehabilitation and replacement of a key structure, where the owner wanted to preserve, replace, or repair part of the structural elements due to a severe corrosion problem. So a massive refurbishment and a massive rehabilitation activity occurs 20 years ago, and after 20 years, all the concrete was corroded, which means that this was a major issue in terms of service life. So my team and I did a service life analysis of those reinforced concrete structures, take into account the use of 2 different corrosion inhibitors and 3 different concrete types. So we tested 3 different concrete compositions with 2 corrosion inhibitors to check the service life, and then we could select what could be the best option for repair the structure. So our objective was to select the best solution to improve the concrete service life. So performance-based design was used in this situation. Your question should be, okay, what about design rules? We all of us, we know the standards, we know the rules, but the problem is that the design rules are in general presented as deem-to-satisfy rules. So they don't give the direct insight in the service life, the necessary maintenance, or the probability of premature failure. So you need to use performance-based approaches to solve this problem. So what are the performance criteria that we can consider for the built environment? So it includes the ability of a construction solution or a structure to operate without any maintenance, have non-deteriorated appearance at all times, or even minimize energy consumption in buildings, or minimize agrothermal risks, for example. So usually the performance criteria is defined as limit state. So you know, in the structural codes, we have the serviceability limit state associated with the design service life. So corrosion is an issue, crack with spalling, vibration, aesthetics, etc. From an ultimate limit state perspective, which is associated with the structural resistance, we should take into consideration the collapse, buckling, and loss of stability of the structure, for example. That's from a structural perspective. From a building physics regulation perspective, the boundary conditions are normally associated with energy conservation and with the overall energy performance of buildings, which are also a kind of serviceability conditions. So these are some examples of limits. The heat transfer by transmission, the heat transfer by ventilation, internal heat gains, solar heat gains, indoor quality. So all of these you already know, of course. So performance levels depends on the action and on the strength. So the measure of risk associated with the specific event of the strength being lower than the action can be expressed as the probability of failure. So a good way to look at the problem is to compare the service life of a specific construction solution using the performance model with the desired service life. Okay. Back again to the case study. So this is a key structure, and of course we wanted to design the repair activities in order to ensure that the structure presents a target of 100 years. That's the working life that we expect. From European regulations, we know that the maximum acceptable probability of reaching the steel reinforcement corrosion could not be higher than 2.3%. So assuming 100 years and assuming that the probability of failure cannot be higher than 2.3%, we tested different we did several modeling tests of the concrete elements of the structure, exposed to different environmental class. Carbonation and chlorides is important for us. For you, maybe sulfates also. And then 3 scenarios were defined for each concrete composition. So we tested plain concrete, concrete with aided admixture inhibitor, and concrete with surface applied migration inhibitor. So, and then what we did, so at the lab we got the physical and mechanical characteristics of 3 different types of concrete, as I mentioned before, and these are the results at 28 days. So we tested the concrete with cement type 1, cement type 2, which include 88% of silica foam, and cement type 4, including 40% of fly ash. Okay, so in this previous situation, the principal degradation mechanism of the structure was the steel reinforcement corrosion. So what is the action and what is the strength or the resistance here? So the action is what promotes the corrosion. It's the CO2 and the chlorides. And what can resist against this corrosion? The cover of the concrete, the chemical and mechanical characteristics of the concrete. So we use the 2T model of reinforced concrete deterioration under the environmental action of carbonation, which is Xc and chlorides, Xs. And the 2T model includes the prediction of the initiation time. So you have here the initiation time and the propagation time associated with the process. So the initiation first period that is mainly dependent on chlorides and CO2 penetration, and it's the penetration of the aggressive agents into the concrete cover that creates the steel depassivation condition. As long as we get the steel depassivation, the steel rebar depassivation, we start the period of propagation. So this period of propagation is initiated with the depassivation and ends when a certain durability limit state is reached, producing reinforcement corrosion. And we can increase or decrease the period of propagation by exposing more or less the concrete to oxygen, to moisture, and to different ranges of temperature. So what is the role of corrosion inhibitors? So considering carbonation environments, the variable that is changed in view of the presence of corrosion inhibitors is the corrosion velocity. It tends to decrease. What about chlorides environments? So in chlorides environments, the corrosion inhibitors, they can change the chloride thresholds, which is important to increase the initiation period. And they can also reduce the corrosion velocity that will affect the propagation period also. So two types of corrosion inhibitors from a company were analyzed, added as an admixture to fresh concrete that I will call AACI, which is only possible to use by replacing contaminated concrete mass. And then we compared that performance with the performance of a surface applied migrating, that I call MCI. Okay, so these are the experimental results of corrosion inhibitor admixtures tested. As you can see, it is expected an increase in chloride threshold up to 54% for AACI and up to 72% for MCI, and a decrease of the corrosion velocity of 83% using an AACI and 46% for MCI. So the present study focused on the most aggressive exposure environment. So do you also use this equivalent class? You don't know this, what is XS1? So probably you have a similar, in your Indian codes, you have a similar way of classifying the structures. So an XS1 is the deck of a bridge, for example, which are areas exposed to airborne salt but not in direct contact with seawater. So that's the deck of a bridge. What we call XS3 is tidal splash and spray zones, which is these columns here that receive the waves, and XS2 is below, it's underwater. Okay, so of course we didn't test underwater, sorry, because that's the best solution. That's the best condition in terms of corrosion minimization. So if you minimize the corrosion for XS1 and XS3, that's fine. So we did the service life calculation. So this graphic here presents the design service life, which are the black bars, okay, for each concrete composition with or without corrosion inhibitors. And on your right, you have the initiation period. So basically, design service life is the sum of the initiation period and the propagation period. You can see that the initiation period is the gray bar, and the small ones, the blue ones, are the propagation period. And this graphic is only for the exposure class XS3. We tested the concrete cover of with 60 millimeters and 65 millimeters. So the first graphic that I show here is the concrete with 60 millimeters of concrete cover. The first concrete is the one with the cement type 2 without any type of corrosion inhibitors, with the corrosion inhibitors mixed in the concrete formulation, corrosion inhibitor applied on the surface, and then again cement type 4 without, mixed, and applied on the surface. Okay, so you have the same here, but with the concrete cover of 65. So basically, increasing the concrete cover has more impact than adding an MCI or an AACI. So we should take that into consideration sometimes. Okay. As you can see, there is an increase of service life if we increase the concrete cover. However, the cement type 2 AD is the best option for a concrete mix with a cover of 60 millimeters and with AACI corrosion inhibitors or MCI type. What you can observe from this is that the main contribution is for the initiation period, not for the propagation period. So what about the balance between embodied carbon and service life of concrete? So what do we know about embodied carbon of construction materials? First, you know that each maintenance intervention is characterized by its longevity and embodied carbon. Second, we know that repairs with low life expectancy have a high carbon impact. And then we know that the cumulative effect of these types of maintenance actions increase the total embodied carbon expended, which leads not obtaining the required longevity. So, and I tried to write in Hindi. I hope you understand. I was trying to write, did you know? I hope it is correct. So why is it important to reduce the embodied carbon of construction materials? Because it reduces resources and associated costs, but also alleviates longer-term risks around resource availability. And sometimes resource availability is also an issue in your country. So we compared the performance in terms of service life of the concrete compositions. I show as an example one graphic here. And you compare the concrete design service life with the embodied carbon expended in kilograms of CO2 equivalent per ton of concrete produced. So as you can see, the design service life are the blue bars that you can see here, and the embodied carbon expenditure are the lines for each concrete composition used in each repair action, and the graphic that I show is for an exposure class. It's the tidal splash zone of the columns. Okay, so we know that eco-efficient changes in the concrete composition like cement 2 lead to minimum value of embodied carbon. So what is the main conclusion? The main conclusion is that eco-efficient changes in the concrete composition led to minimum value of embodied carbon and were associated with an increased service life. So it seems that development of biocomposites, in this situation bioconcretes, are a possible solution for this problem. So from another perspective, another point of view, I will present a case study where the issue was not structural, as the corrosion problem that I mentioned before. The issue here was the energy efficiency of the buildings that belong to a social neighborhood. So these are 28 apartment blocks from the 90s belonging to a social neighborhood, and retrofit works had to take place in order to repair the existing defects in the construction and improve the energy efficiency and indoor comfort of each building. So what was the challenge? we evaluated the agrothermal risk of several refurbishment scenarios with and without bio-based solutions. And then we implemented a probabilistic approach, like a performance-based design again, for the design of solutions for building thermal retrofitting. And then it was decided to design for a minimum indoor temperature equal to 18 degrees based on the agrothermal monitoring and energy audit that we did during 2 years for these buildings. We realized that in order to ensure that relative humidity was always lower than 70%, to ensure health, that there was not health problems for people, it corresponds to a probability of failure of 20%, which leads to an optimum minimum design temperature of 18 degrees. Because the majority of these houses, the indoor temperature was around 14 degrees. So as you can see, it was very difficult to survive here during winter. So the development of innovative bio-based materials for thermal retrofitting enabled to increase thermal insulation up to 40%. So what did we test? We did some laboratory tests using different bio-based materials, namely a very famous one in Europe, which is cork. I know that we don't have cork here, I think. So cork is in fact mainly, 50% of the cork comes from Portugal, is exported from Portugal, and it comes from the trees. And then we incorporated the cork granulates into new mortar compositions, and we compared with traditional solutions. We realized that the thermal insulation could increase up to 40%. We realized that there was a reduction of the CO2 emissions and the embodied energy up to 30%. And we realized also that these type of solutions could minimize the impact of retrofitting solution service life to less than 30 years, which highlights the importance of durability in the analysis of energy efficiency in buildings. Okay, so basically, following these two examples from durability perspective and from energy perspective, this is what we have been doing at our labs, designing of bio-based composites for retrofitting and refurbishment. Of course, that we realized that the use and the need of using biotechnology concepts was crucial to increase the performance towards a better durability and towards a better energy efficiency. So basically, this is what we are doing. Trying to promote energy efficiency with smart materials, mainly in buildings, but also tackling the problem of durability of structures, because the impact of that industry is really high. Finally, I would like to announce, probably you will all know, but just in case, I'm one of the editors of the Proceedings of Institution of Civil Engineers journal called Engineering Sustainability, with an impact factor of 0.34. And you are all welcome to publish here. So this Engineering Sustainability journal provides a forum for sharing the latest research and practice of sustainability principles in engineering planning, design, and application. And the exposure is up to 90,000 IC members and over 1,500 subscribing universities and industries worldwide. So thank you very much for your time.